let's just start with the matrix. I'm going to focus on the process. I haven't even worked this one out or anything, so I'm hoping that we actually get something. But what's nice about this stuff is that we can always just multiply things back out at the end and check if it works. So that's the good news. Unless it doesn't work, and then that's just annoying. But this is our matrix. 1, 2, 1, 2, 3, -4, 3, 1, -2. And so we have 1, 2, 3 rows and 1, 2, 3 columns. So it's a 3 by 3 or a square matrix. And I'll just say ahead of time that I believe this will work, but not all matrices can be factorized as an L and U. But we'll talk about conditions later on. So our goal is to break this down into two matrices, a product of two matrices called L and U. Surprise, surprise. And it's kind of like when you factor a number. When you factor, let's say 6, and you get, okay, 2 times 3 is 6. So 2 and 3 are factors of 6, and so are 1 and 6. But you get the idea. You're decomposing 6 into a product of two numbers. So it's the same thing when you factor a matrix. You're looking for two matrices that multiply that give me this one. But not just any two matrices. L and U stand for lower. L for lower, 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 and U for upper, upper, upper triangular, lower triangular, upper triangular. And all that means is for the lower one, everything above the diagonal must be 0. So everything above this diagonal is going to be a 0. And everything on the diagonal or below can be any real number, thereby making a triangle like this that's on the lower half, therefore lower triangular. And so for upper, you guessed it, everything below the diagonal must be 0, and everything on the diagonal or above can be any real number, like this. So that makes an upper triangle like that. And so this is for the 3 by 3 case. So our diagonal is going to have 3, and you fill in the rest. But, you can apply this for 2 by 2 or 4 by 4, etc. So just remember, for lower, it's everything above the diagonal is 0, and for upper, everything below the diagonal is 0. So our matrix is going to have this form and this form. So I actually meant to make this video back when I made a linear algebra video on Gaussian elimination, and we'll have more fun with this too in the future. But it goes hand in hand, because in this case, we are going to take A and we are going to make it into row echelon form. Row echelon form. And if you remember from that video, row echelon form actually happens to be upper triangular because of the definition of row echelon form. So for the non-zero rows, the 0 rows are all going to be on the bottom if there are any. But for the non-zero rows, all the pivots are going to be, it's always going to be to the right of the row above it. And so that's going to be, by definition, upper triangular. And it actually just occurred to me, a long-time subscriber, Ari, actually suggested this at the time when I made that video for LU, and I thought it was brilliant, but I never came back around to it. But that's what we're going to do. We're going to use Gaussian elimination for A and is usually allowed, but in this case, since we want to make sure that this matrix is lower triangular, you're not allowed to swap rows. Furthermore, when you do the row operations to get the row echelon form, you kind of want to focus on moving downwards like this, so you don't want to like work back upwards. So once we have this 1 as a pivot here, you kind of move downwards. So I'll show you what I mean. So let's see here. So we're gonna keep our 1, 2, 1. So let me just, I guess we'll just copy this matrix first. Again, just to have it in one place. So 3, 1, -2. Okay. So the first thing I'm going to do is, I already have 1, 2, 1. That's fine. This 1 can stay 1. So I want this place to be a 0, right? So the next row is going to be row 2, and I want row 2. I'm going to replace that with row 2 minus 2 times row 1. And I get that by looking at this 2 and comparing it to the 1. So 2 minus 2 times 1 gives me 0, and that's how I know what I'm going to do to the entire row. I want this to be a 0. So I keep my 1, 2, 1. 2 minus 2 times 1 is 0. 3 minus 2 times 2, so 2 times 2 is 4. 3 minus 4 is -1. -4 minus 2 times 1 is 2. -4 minus 2 is -6. And then I'm going to go ahead and keep my 3, 1, -2. Good. Then the next thing is, since this is already 0, I'm going to make this one 0 by doing something very similar, right? So I'll just keep my 0, -1, -6. And then I'm going to do row 3. I'm going to replace row 3 with row 3 minus 3 times the 1. So replacing row 3 with row 3 minus 3 row 1. So that makes this a 0. So 1 minus 3 times 2, so 3 times 2 is 6. 1 minus 6 is -5. -2 minus 3 times 1 is -5. Don't forget the multiplication first, right? So 3 times 1 is 3. -2 minus 3 is -5. Good. And then, again, we're not going to necessarily make this reduced, so we don't need to have this be a 1. We're just going to leave it as is. But we do want this -5 to be a 0 now. So we're going to do 1, 2, 1, 0, -1, -6. And now I want to do comparing -5 and -1. I can do row 3, replace that with row 3 minus 5 row 2, because -5 plus 5 is 0, and in order to get the -1 to a plus 5, I have to multiply by -5. So I'm going to replace row 3 with row 3 minus 5 row 2. So 0 minus that 0 still. And then this is going to now be a 0. So now we have a new pivot. So -5 minus 5 times. So -5 times -6 is positive 30. -5 plus 30 is 25. Ta-da! So that's it. And that is row echelon form. Because we have no non-zero, or we have no all 0 rows, and every row, the first number that is non-zero is to the right of the row ahead of it. So 1, -1, and 25 are pivots, and they are to the right. And this is actually upper triangular, because everything below the diagonal is 0. So this is our U. So we already got U, which is great. But how on earth do we get this is where it gets a little bit messy, but it's not too bad. So what we basically did is we have a bunch of elementary operations, and we can represent each of these as elementary matrices. So we're going to say this is E1, this is E2, and this is E3. And the three sort of matrices that correspond to this is where it can be a little bit confusing, but all you do is rewrite like E1 as a matrix. So in order to replace row 2 with row 2 minus 2 row 1, you keep basically the identity matrix. So the identity matrix would be like this, 1 in the diagonals and 0 everywhere else. But since we are replacing row 2 with row 2 minus 2 row 1, you actually put a negative 2 here for the negative 2 times row 1, and then that's it, and then you keep the identity matrix. And so if you picture this as a matrix, what that means is if I multiply, let's say I just have like A, B, C, D, E, F, G, H, I, just for some intuition here. The 1, 0, 0 and the 0, 0, 1 part keep this and this. But for the second part, if you remember matrix multiplication, you multiply this row by each column, then this row by each column, then this row by each column, and you multiply and then add corresponding terms, right? So for this row, you would do negative 2a plus d, so that would be negative 2 times this first one, and then for the next one you have negative 2 times this one and negative 2 times this one, which makes it negative 2 times the first row, and then plus the 1 is the R2 part. So if you're not familiar on how to create elementary matrices, we can come back to this, let me know, but if you want to. But that's kind of the idea. You can just multiply it out to prove to yourself. But each of these basically only involve one step. And so notice that that is lower triangular. And so for E2, it's the same idea, but we are replacing row 3 with row 3 minus 3 row 1. So again, you can just kind of lightly sketch in your identity matrix, which is just 1 across the diagonals, 0s everywhere else. But for row 3 being replaced with row 3, so I'm going to look at row 3, and I'm replacing it with row 3 minus 3 row 1. So since it's minus 3 row 1, this first item here I'm going to put as negative 3. So that when I multiply something else, it'll be negative 3 times the first element for each part, so that'll end up being the first row there. And then plus row 3, so that's what this one is for. So you're just basically replacing one item in each of these. Okay, like that. So that's E2, and then the last one, same idea again, is row 3 being replaced with row 3 minus 5 row 2. So again, I'm going to sketch in the identity just to start somewhere. And then I have row 3 being replaced with row 3 minus 5 row 2. So since it's row 2, I'm going to change this corresponding one here to be negative 5, like so, like that, and then keep everything else the same. So if you can picture it, when you multiply by something, the first part's always going to go to 0, but the second term is going to be what's negative 5, so for each of the second row, and then plus the third, like so. Okay, so I'm going to go ahead and rip this this out just in case we get cut off here, but we will refer to it. So there's that. Okay, so basically we have all these matrices. These are like transformations almost, and we're just gonna multiply. Like what we end up doing is we're multiplying A by these in this order. So first E1 times A, so we're basically doing like this, A being that matrix, our original matrix, and then we multiply by E2, and then we multiply by E3, and in general you can just do it to EK, however many row operations we did, but in this case just these three, and we got U. And so since our goal is to get A in terms of LU, we basically combine those to try and figure out what L is if we move it over to the other side. Now, there are a couple of theorems that we have to count on. One is that all elementary matrices, so where we just have one row operation off of the identity matrix, those are all invertible, meaning you can have an inverse. And the other thing is that the product of invertible matrices are invertible. So this whole thing basically is going to be my L inverse, and then I want to move it over here so that I can find what L is. So in other words, I'm going to take the inverse in order to move it over, so to speak. I'm going to take the inverse of this thing, like this, and in order to find that inverse, you actually take the inverse of each piece in the backwards order. So this is E1 inverse, E2 inverse, and E3 inverse U. And so this is going to be L. And since each of these operations are lower triangular, then this thing is going to be lower triangular. And we know these are going to be lower triangular. The elementary matrices are lower triangular because of the fact that we didn't do any row swaps, and we kind of focused on going this way for Gaussian elimination, downwards. So once we set one as a pivot, we don't work back up that way, okay? So that's how we know that this is going to stay lower. So what's cute about this is that there are some tricks that we can use to find E1 inverse and E2 inverse and E3 inverse, so we don't have to calculate it the way that we normally would, which is to take our matrix and then put a line and then put the identity 1 0 0 0 1 0 0 0 1 and use row operations to get this side to be the identity matrix and this side would be the inverse. We don't have to bother with that in this case because these are elementary matrices. So really, when we take the inverse of E1, for instance, this 1 0 0, -2 1 0, and 0 0 1, we just replace this -2 with the positive 2. And intuitively, it's basically because to kind of undo the row 2 minus 2 row 1, we're just going to add the 2 row 1 back. Okay, so when we do this inverse, and in this case, since all of them are like that, we're not scaling anything. We just go ahead and swap the -3, the -5, the -2 to be a positive. And if we were to scale a row, for instance, if we were to say, 1/5 row 2, like replacing row 2 with 1/5 row 2, then you just make it 5 instead of 1/5. But in this case, we don't have that. We have all replacement ones here. So we're just going to swap when we actually try and calculate this. So in this case, we're just going to do 1 0 0 pi positive 2 instead of this negative 2. 1, 0, 0, 0, 1. And then same for this 1, 0, 0, 0, 1, 0, 3, 0, 1. And then 1, 0, 0, 0, 1, 0, 0, positive 5 and 1. And then u is going to be the u that we calculated, which is this 1, 2, 1, 0, negative 1, negative 6, 0, 0, 25. So now we're just going to multiply it out. This ends up actually just being smushed together. You can have a 2 here, a 3 here, a 5 here. But we can just work it out just to show it. So we go 1, 0, 0 times 1, 0, 3 first, meaning 1 times 1 plus 0 times 0 plus 0 times 3. So that's 1, and then 0, and then 0, and then 2 times 1 is 2 plus 0 plus 0. 2 plus 1 plus 0, or 0 plus 1 plus 0 is 1, 0, 0, 0, 0, 0, 3, 0, 0, 0, so that's 0, and then 0, 0, 1, so like that's the first part. And you can take your time with this, of course, but or let me know if you want to review matrix multiplication, but I actually will link my other video on that. But the zeros make this kind of nice. But you have 1 times 1 is 1, 0, 0, so 1, and then you have 0, and then you have 0, and then 2, 0, 0, so 2, and then 0, 1, 0, so 0, nope, 1, and then 0, 0, 0, and then 3, and then 5, and then 0, 0, 1. So like I said, basically this 2 goes here, the 3 goes here, and the 5 goes here, so it does get all smushed together, but I just wanted to write that out anyway. So notice this is our lower triangular. Everything above the diagonal 0, and the other terms are whatever, any other real number. So we have our u, which, just to copy over from this, is 1, 2, 1, 0, negative 1, negative 6, and 0, 0, 25. So that's our upper, and this is our lower. And notice that when we do the operations, we go E1 and then E2 to the left of that, and E3, but when we take the inverse, you multiply this way. E1 inverse, E2 inverse, E3 inverse. And so that is our answer. Now, I haven't worked this ahead of time, so I have no idea if this is right or not, but let's go ahead and check this. Let's go ahead and check whether or not it gives us our actual answer. So like if you were to factor 6 into 2 and 3, you can just multiply to check to see if 2 times 3 is 6, and that is true. But let's try out 1, 0, 0, 2, 1, 0, 3, 5, 1 times 1, 2, 1, 0, negative 1, negative 6, and 0, 0, 25. And let's see if we get our 1, 2, 1, 2, 3, negative 4, 3, 1, negative 2. So this is where you have to be careful. 1 times 1 is 1. 0 times 0 is 0, 0 times 0 is 0, so just 1. 1 times 2 is 2. 0 times negative 1 is 0. 0 times 0 is 0, so just 2 in the next one. 1 times 1 is 1, plus 0 times negative 6 is 0. 0 times 25 is 0, so we just have a 1. So far the first row looks good. Then we have 2 times 1 is 2, plus 1 times 0 is 0, plus 0 times 0 is 0, so we have 2. 2 times 2 is 4. Negative 1 1 times -1 is -1 and 0. So 4 minus 1 is 3. So that's good. Then we have 2 times 1 is 2 minus 6, because 1 times -6 is -6 and 0. So 2 minus 6 is -4. That's good. 3 times 1 is 3 plus 0 is 3. 3 times 2 is 6 minus 5 is 1. So that's 1. 3 times 1 is 3 minus 30 plus 25. Ooh, that's too much. 3 minus 30 plus 25. So that's 28 minus 30 is -2. So we have 1, 2, 1, 2, 3, -4, 3, 1, -2. Oh, thank goodness. Thank goodness. Yay. So we did it. So this is our L and this is our U. And so we have officially done our LU decomposition for this particular matrix. So I hope that's making sense. The big picture is to turn A into row echelon, which is going to be my upper and my upper triangular matrix. For the lower one, I basically keep track of each row operation, make sure you're never swapping, and make sure you're moving sort of downwards, right? You set your top pivot and you move downwards, making the rest zeros. Then you keep track of the operations that you did and translate them into elementary operations, which just means that you're doing one thing from the identity. And when you translate, just take your time with this part if you're not used to it. But make sure it lines up with which row you're replacing, and then align what you're adding to it. So we have E1, E2, E3. Then what we do is we want to take the inverse of the product of E1, E2, E3, but we are multiplying left this way. So when you take the inverse to get your L, you end up taking the inverse of E1, E2, and E3. So each of those, but you're going to do it in the forward order. So E1 inverse, E2 inverse, and E3 inverse. And when you take the inverse there, you can use the shortcut of, in this case, since we're not scaling, we're doing the, combination. You can just go ahead and change the negatives to a positive. So like a -2, -3, -5, and just leave everything else the same. That's a little shortcut. And then you can multiply those together. It ends up just as another shortcut. There's so many shortcuts here just because of the property of a lower triangular matrix and how inverses work. But when you multiply these three, they actually end up just squishing together. So this 2 and this 3 and this 5 get squished together. But if you want to just multiply it out, you can go ahead and do that. That gives you a lower triangular matrix, and that is your L at the end. And so, again, E1, E2, E3 are going to be lower triangular because of the fact that we didn't switch anything, and that's why it's important to work top down when you're doing the Gaussian elimination part. But there are multiple ways to do it, of course. But if you do it methodically this way, you'll just make sure that it really is lower triangular. That way when you take the inverses and all that, it doesn't get all messed up. So that's it. I thought this was pretty cool. It has really been a long time since I've done anything with this, so it was fun to kind of look back on. And we can dig a bit more into it and look at which matrices can do this and when you can't. But as we kind of talked about, if it involves a swap, if you have to switch to get it to row echelon form, then that gives you a clue that you cannot actually do this. You need one more thing, which is to do some kind of permutation. But this is really cool because this is what I believe there's a lot of computer applications to this, because it uses this for certain systems of linear equations about it is you're kind of always doing this waterfall substitution kind of thing, but we can come back to this another day. But I hope that this was interesting. This was a 3x3 case, but like I said, not all matrices can do this, but if you can, it's going to be a square matrix, so you could try 2x2 or 4x4 or something like that. Just generalize what we did, and remember your definitions of lower and upper triangular. And yeah, let me know if you have any questions, and I will see you around for more math very, very soon. Thanks so much for joining me. If you are asleep by now, sweet, sweet, sweet dreams. And subscribe if you haven't